Your current AI agents can be now 92% smaller and even 15% faster with this new distillation approach called Structured Agent Distillation, which got pre-published a couple of days ago. And in this demo, I'm going to show you how you can utilize their approach to let your current AI agents, which they're potentially running with large language models, you can use this technique to use a small language models to empower your AI agents to do the same thing with even same accuracy and performance, but significantly save cost and plus have much more faster solution. Then let me show you how. Just last week, group of researchers from different universities, namely Georgia, Florida, MIT, and Harvard, they came up with a new approach that how you can have small language models being used for creating your AI agents, but with potentially same performance that you get when you use large language models for your AI agents. You might guess an approach called distillation, which is a technique to teach your smaller model through the power of larger model. But this time they have done that for agentic frameworks and approaches. And of course, there are some distillation approach that how you can train your smaller models to be your agents. But this time they have a new distillation approach called a structured agent distillation. So before I dig into actually their approach and how you can utilize it for your projects, let me provide you a walkthrough on what's the challenge they are trying to resolve and what are the similar challenging solutions. So why this one is much better and what's the outcome for you. So with this approach, they were able to actually create AI agents that are initially 92% smaller than agents that you could create with large language models. But they said that the AI agents could do the same thing with same performance. So why be bother and go and pay for those larger models that they are generic enough while I can still create my own AI agents that is distilled from or trained from large language models. And to do that, a smaller scale of these student models that they learn from their teacher, which is the larger model, you can have also your AI agents to be 15% minimum. That's what they shared, even faster. And the latency gonna be diminished as well. So what is the problem? When you create your large language models, your AI agents with large language models as of now, they are too large. So having too large solution, that means first of all, you have to potentially pay more. And some of these large models, because there's a huge pre-processing and pre-processing happening for doing the action or proposing the action for agents, they are then definitely slower as well. So having a slower agent is one challenge, and paying for larger models is another challenge as well. So how we can resolve that with this structured agent distillation? There are some previously traditional approaches for distillation. That means you can have your AI agents being trained and learned by a larger model and have a smaller model to act as your AI agent. But that token level distillation, which is the typical approach as of now before this process that they mentioned in the paper, you just learn technically the token. That means here, for example, I have a larger model that is doing something, doing some actions here, and here's my training data set, and I will give it as is to a student model, which is a smaller model, to learn the same thing and do the same thing, like having the same action for my AI agent. But because you're just throwing the token as is, the problem is the student only learn what to do, not why to do. And this is very critical because when we do actions by agents, we need to make sure that that model will understand why and then provide the proper action to be in place. So what is their solution? They're saying that we are not going to do token level distillation. Instead, we're going to have a trajectory created, which is our larger model, which we call a teacher as of now. We will have its reasoning and then the action that decided for our AI agent. So two things, reason and the action. Then we split these two in two parts, which is again reasons and actions. And then we teach this smaller model to understand not only what proper actions should be done based on the user question, but also the reasoning behind those actions. And because these reasons and actions are coming from a larger model, that means our smaller model is learning not only proper actions to do as our AI agent, but also the reason behind, which is the critical or secret sauce of their approach. So to give you an example, here is an original teacher output or a larger model. Let's say we ask that, hey, do some changes or find something in an environment. Let's say it says, oh, I need to find the soap. So I'm probably in the bathroom. It's probably in the bathroom. I'm going to go to bathroom. And now I can see the soap on the counter. So pick up. So you see that there are some reasonings and then there's an action and then it got the soap out. So we will split that in two trajectories. First, reasoning here that have the reasoning segments. I need to find the soap, all the same tokens. And then on the action side, we have go to bathroom, pick up the soap. So two actions and a couple of reasonings for those actions. This is the first step towards this structured distillation, which is the approach proposed by the paper. And then how do we train? Here is the second change or new approach they're providing, which is a loss function or fine-tuning that a smaller model to be used as your smaller AI agent. Now our total loss is not just the token level or how different the smaller model token is compared to the larger model. Obviously, they should be the same because smaller model are going to follow the larger model. But here we have two loss functions. First, how close we are in the reasoning. That means a smaller model or agent can reason like the larger model. And the actions decided by a smaller model if it's close like the larger model. So with having these two sum, now this is our total loss. So this is the second thing they're proposing in the paper. And moving further, they summarize the results. They were able to actually distill some of the larger models. I think they used GPT-2 and GPT-3 as an example. And they created an AI agent with just models with 120 million parameters compared to GPT-2 and 3. That means 92% almost a smaller model. And they got success rate of 5.6% better compared to other distillation approaches. So if you choose this approach compared to typical fine-tuning token level distillation, you will potentially lose that performance. So their approach is on average above all different approaches has been used so far in different use cases they utilize in the paper that I'll talk about that shortly. The speed, because now you have your AI agents running with the smaller models, you can have up to 50% faster. And in general, the reasoning match got almost 77.9%, which is 5.5%, again, better compared to other approaches. So here is, for example, as an example, find the soap. Now we have this smaller language model providing the same reason, right action, similar reason, and the right action. So smaller AI agents, but do the same thing and same approaches. So what is the key takeaway here before I jump into the more details of the approach and how you can utilize it in your own codes? They're saying that with teaching these smaller models, the reasoning and the action, we can get the same performance. But this time, we are not just fitting these tokens to the smaller model to learn and act like the larger model. We provide the reasoning and the action. It's very important to provide both of them or supervise the model on both paths, not just the average token. And because now you can have your AI agents smaller, we can deploy it anywhere. We can have on IoT devices, phones, and even do it for edge computing, which is not possible if your AI agents as of now is using large language models. So faster and better performance potentially with these small models. And lastly, easy to implement. So their approach is very straightforward and it's very easy also to understand. So let's dig into that in more details. All right, so let's start with how you start creating this training data set for training these small models to have it as our AI agents. So technically what they did for different AI actions, obviously for use cases, you have different type of workloads and actions, but in the paper, they use a couple of well-known environment and agents called Off-World and Web Shop, which are an environment like a kitchen or a house. You can pick up items. This is good for robotics. And Web Shop is technically an AI agent supposed to fulfill a purchase of a product or something that you specify, which is an AI agent as well. So what you're doing is that we will realize what larger model will do in these use cases. We will get their reasoning and also the action. And they prompt that larger model. When you want to provide your reason, start with the keyword reason. And when you want to do action, start the keyword by action. So that action can be called that tool, called that function, called that database. These are the tools you specify in your AI agents. And here that larger model is deciding that. So we grab these two and we segment them through something like maybe just a simple parsing. If anything is started with reasoning, that's the reasoning part. And anything is started with actions, this is the action part. That's pretty much simple. Then with having that segmentation done, we need to tokenize both segments of reasoning and action. So we have the tokens of reason like R1, R2, all the way to RK. Same thing for the actions. And then when we have it in place, we are going to mask these tokens. This is very critical, and I'm going to tell you why. But what is masking? So if any token of this above belongs to reasoning part, we will put number 1, else 0. Same thing we do for actions. If any token from the above belongs to action, we put 1, the rest is 0. Why we are doing this? Because with having this masking in place, when we update the gradients or I'll calculate the gradient, we're going to cancel out the effects of reasoning when we tune the model for reasoning, and we cancel out the effect of the reasoning when we tune the model for acting. So that means we separate these two components and make sure our distillation approach is teaching the smaller model for both of them. And I will show you in the code how these masking comes in our loss function calculation. So long story short, we have now two sub-loss functions. One is reasoning, and we need to have this chain of thought loss, which is the reasoning of the larger model, very close to the smaller model. On the right side, we have the loss term for action. And here, we got to make sure the action chosen by smaller model is exactly like larger model. That's really our approach. And then, as I mentioned, the sum of these two going to be our loss function. But again, this is a single training process that in parallel, we teach the model both acting and also reasoning. Moving further here, what we're going to do, I'm going to show you why this is not just a typical token level distillation, and this is slightly different than other distillation approach you might have heard or seen for AI agents. First of all, we have separate functional roles between reasoning and acting that we just discussed. Second, we have independent learning. That means it allows the students learn both logical reasoning and acting independently because of that masking and separation that I told you about. And also for preventing any gradient leakage, we provide that mask, which is also helpful. So we do not care about the distribution of the token differences when we see the smaller model outcome versus the larger model. We see the distribution of the tokens for both reasoning and also action. This is also different with just a token level distillation. Alright, so here's an example to show you a little bit more samples to make it a little bit more tangible. Here, for example, our teacher or larger model, we're going to do an action as an AI agent. So here we have the reasoning, and then we have the action here, which is go to kitchen. And then we have the tokenization and masking. So we tokenize the reasoning, I should find the fridge. Same thing for the action. And because these tokens are for reasoning, we put 1, the rest is 0. Same thing for action, we put the rest 0 and put the action 1 as 1. That's it. This is our masking. So, couple of questions that might come to your mind as of now that I'm going through this approach. So let me answer them if in case you have these questions. Do we train two different student models, one for reasoning and one for acting? No. It's just a single model, single distillation or single fine-tuning, but we have our loss function considering both steps or segments. Is reasoning and acting mixing the same training data? Well, we just show you that the raw input sequence contains both actions and reasoning. However, we need to label them as reason and act because they will have different loss functions and we need to sum them up, and then we need to have the masking be in place. But make sure to understand that this is not as same as uniform token level KD distribution measurement, which is an approach to see how two distribution of tokens are similar to each other. So this is absolutely different. If both are in one sequence, is any traditional token level? We already discussed about that. This is a segment-aware masking approach that we apply for distillation. So obviously, no, this is not just considering tokens. This is considering both reasons and actions. All right, so here are a couple of hints that what you need to apply to your current fine-tuning or distillation if you're doing typical distillation. The first thing is that in your data set, in your fine-tuning data set, right now maybe you just have your plain text, but you need to apply those Boolean masking as well that include reasoning and acting. On the loss function right now, maybe you just have the KL divergence calculation that treats all the tokens, everything equally, but you need to change that with the new loss function that include reasoning loss and action loss. For training, if you use some Hugging Face packages or any agentic framework packages that let you do distillation for language models, you need to double check if you need to edit or change that compute loss function. I will show you a quick example with PyTorch how you can implement this approach. And lastly, for your model optimizer or scheduler, you don't need to change anything given that you already have changed your loss function and also you have changed your fine-tuning data set with that masking approach I told you about. All right, here is just a quick code snippet. This is just an example of how you will apply this loss function when you fine-tune the model with this approach. So here we can see I have the input from or the output from the larger model that we want to learn from it. We also have the current output of our smaller models, which we are going to fine-tune it. And here I have also the masking for both reasoning and acting that I told you about. So I will go through all these examples of masking to compare our smaller language model with the large language models and to calculate the differences. And to calculate the differences, we are calculating the mean of all these differences for both acting and reasoning. And this is the new loss function that sum up all of them and we return it back. So technically, we are just going to optimize this to minimize the differences of reasoning and acting for the distribution of their tokens, which technically what we're doing here. All right, to wrap up, what we learn here is that you don't need to necessarily choose large language model to create your AI agents. You might start with large language models because you want to make sure your AI agents, they're acting precisely, they have a good performance, they're smart, and they choose the actions or right tools or right database as you provide them access properly, let's say through MCP. But there's a great chance that if you fine-tune smaller models, let's call it distillation, by how these larger models are behaving, you might get the same performance. But the trick here is you do not need to just have the output prompt of larger models to fine-tune a smaller model. You need to provide the output, which is reasoning, and the action that the larger model decided to choose. So with having these two in place and have that included in parallel, when you fine-tune a smaller model, this is the winning solution that you will get a smaller model that acts like a larger one for your AI agent and they can do actions with the right reasoning, even if they choose maybe by luck the right action, but it's not just luck. You have provided the right reasoning as well to those models to be able to provide the action for you properly. All right, that was all about this video. If you enjoyed and you found it helpful, I appreciate if you liked the video and share your thoughts, questions, and comments in comment section below and subscribe so you don't miss the next video. Thank you so much.